Following the success of the last 7 years' conference video proceedings, the 1997 IEEE International Conference on Robotics and Automation has issued the 7th Conference Video Proceedings. The purpose of this video proceedings is to present new and significant experimental results in robotics and automation undertaken by the international robotics community. The effort is intended to enhance and complement the theoretical results in the technical sessions of the conference. A total of 37 entries were submitted, and 32 were selected, revised, and edited into this final videotape.
Grouped into 8 categories, the 1997 IEEE video covers such topics as interactive human-robot supervision, non-telemanipulation, full-scale mobile research robots, robotic subsystem sensing technologies, micro-robots, control dynamics and kinematics, telemanipulation, computer-aided design and simulation, industrial applications.
Interactive human-robot supervision, non-telemanipulation. Virtual tools for robotic supervision, USA.
Penn State Department of Industrial and Manufacturing Engineering. In Dr. David Cannon's Virtual Robotics Laboratory at Penn State, students work at perfecting a computer program which controls robots as they perform tasks dangerous to humans, like the handling and disposing of hazardous waste. The program employs a cutting-edge concept called interwoven reality.
Okay, in the case where we're doing flexible manufacturing, we want to be able to quickly set up new tasks, to make new products, and we want to be able to reach in and tell our robot, I'd like you to take the part here and put it in that orientation there. We don't want to have to shut down the plant and go out with our goggles and our hard hat and use a teach pendant to drive the robot through its motions. We'd like from a remote location to simply reach out into the environment. In this case, we use a glove that's got a cyber glove with sensors in the fingers that allows us to reach in and grab virtual tools and say, I want to put that part in that machine in that orientation. Specifying endpoints only and letting the robot develop its own trajectories based on obstacles that it perceives in the scene. We built a camera tower with 2 cameras, one on top and one on the bottom, that can spin around and rotate so that we can see anywhere in the 360-degree sector and target any location by triangulation within that space. So here's pan and tilt of a bottom camera. Within the control room, remotely located in a safe location, we have defined tasks where you can see the camera rotate back and forth to define locations by clicking in that scene. So as we click in the scene, you'll see it rotate over to the other wheelbarrow that was by the Adept robot. The top view is live and the bottom is still, or vice versa. You can bring that gripper way into the foreground, almost as big as the robot, and you can see the configuration of the tool. He can release that tool anywhere in the space. He can grab it and he can place it, and then he can put his clutch out. When he lifts his thumb, it will leave that tool there, and he can go grab another tool if he would like. He can go back in and grab the tool and move it. He can place it. Now when he puts a single index finger forward, that means put that, and then he can do and that, and however many other that's there, and it will define a sequence of tasks if he wants to move multiple objects. Now Charlie Graves of the Virtual Tools and Robotics Laboratory at Penn State has implemented our latest system of virtual tools at Sandia so that he can reach in, grab, in this case, a slurper tool, place it on the object, and have the robot proceed to do the task. So now a plate of metal that was in this tank that was covered over with sludge can now be exposed using a simple gesture to say excavate there, or an attribute of that virtual tool is to make a rectangular cross-sectional excavation. Now a magnetic gripper tool can be placed over that same object that's now exposed in video, and in the Sandia case we now have a very powerful Telegrip Sancho simulation model that can show us what the robot will do, and we can accept that or reject it. In this case it can be accepted, And now a very careful orientation of that tool to the normal of the plane that was specified using the virtual tools can proceed, and the robot will come down very carefully to the specific site where the object needs to be retrieved. Once the object has been retrieved from this radioactive hazardous waste scene, it is taken to their location that was specified, in this case a bin, so that object can be retrieved from the hazardous waste radioactive site and taken to a safer location outside of the storage tanks.
The JPL Long Range Science Rover team has developed new technologies which enable future long-range rover missions to Mars. A single uplink command cycle to the Rocky 7 rover in the JPL Mars yard will demonstrate the current rover technology. A 180-degree panoramic image set was taken by cameras on the simulated lander and downlinked in the previous command cycle. A terrain map was generated, which maps image pixel coordinates to 3D terrain locations. Generation of commands for the rover is done cooperatively between mission planners at JPL and scientists distributed over the Internet using the Web Interface for Telescience, or WITS. Scientists specify science targets and subtasks to perform at the targets. Mission planners at JPL specify the waypoints for the rover to go through and then uplink the complete command sequence to the rover. The rover receives the command sequence and begins moving to the first waypoint. The rover performs obstacle detection using images from its front cameras and alters its path if necessary to avoid an obstacle. When the rover arrives at the first science target, it executes a goal ID subtask to confirm the target, and then executes a spectrometer read command. The rover automatically adjusts its position to prevent any collision with the rock. The rover deploys a calibration target for the spectrometer, and then takes spectrometer readings through an opening in the front of the arm. The rover then traverses through waypoints to the next science target. When the rover arrives at a specified waypoint, an automated rover localization is performed. The rover tells the lander its approximate location, and the lander points its cameras at the rover and takes an image pair. The rover then makes a slight move, and another lander image pair is taken. The rover location is then computed using a differencing algorithm applied to the two image pairs. The rover automatically updates its position with this information. At the dig and dump operation target, the rover analyzes close-up images of the target area to ensure that it has appropriate soil. If it detected rocks or pebbles, then it would automatically search the local area for a more suitable dig location. It also checks for and avoids possible collisions with rocks. After the rover completes the dig operation, it performs a visual check of the sample. If it does not detect a large enough sample, or if the scoops do not close all the way, then it reports a failure and continues. The rover executes a long traverse at the end of the command sequence. During the traverse, it performs obstacle avoidance every 25 centimeters and uses its sun sensor for heading estimation. In the coming year, technologies will be developed to enable the rover to perform long-range missions independent of the lander. Extensive field tests covering multiple kilometers will demonstrate the integrated rover capabilities.
interactive automation for live power line maintenance by untrained operators. Canada.
For the last 15 years, researchers at the Robotics Division of Hydro-Quebec's Research Institute have used robots to simplify live line maintenance operations. This video shows how tasks can be executed by untrained personnel using a simple, robust interface. To find the pose of an object, the operator selects the object from a database and then points a laser beam on the real object. The system then automatically scans the scene. The result of the pose determination appears automatically in the graphic model. A wireframe model is also superimposed on the view from the end effector camera. The graphic model of the environment allows the user to verify the state of the work cell in real time. In the task menu, the operator can choose from a variety of actions which can be executed step by step or continuously. In both cases, before executing a task, the system verifies a series of preconditions. If this cannot be done autonomously, the user is prompted with a validation question. If any of the preconditions are not met, or if an error occurs, the execution stops and the system sends a descriptive error message. The user interface also gives the operator direct control of the robots. Tool acquisition and release is managed automatically. In order to test the functionality and user-friendliness of our control environment, 3 live demonstrations were held during the 1996 IRIS Precarn Conference in Montreal, Canada. After having demonstrated 2 tasks, 4 volunteers from the audience were invited to execute 2 more tasks. 2 operators first inserted a pole cover, and 2 other operators removed the capsule. This demonstration confirmed the robustness of our robot interface. 12 untrained operators successfully executed the tasks with only 5 minutes of online training. It was observed that 75% of the operators are immediately comfortable in using a 6-degree of freedom hand controller, and that Nintendo generation operators required virtually no training.
Visual Servoing and Visual Space Task Programming, USA.
In this video we will show how to solve some real-world tasks using a robot arm and hand. With traditional calibrated robotics, it has been difficult to solve human everyday tasks. We propose using uncalibrated visual servoing and visual motor model estimation for the motor control. On the high level, task planning and trajectory generation is done in camera space instead of robot coordinates. In the first task, we use a robot arm and hand to pick up, transport and screw in an ordinary light bulb. 2 cameras are mounted to the left and right of the hand. The robot joint motions are controlled directly from camera space. Special markers on the bulb and socket are tracked in both cameras. The controller goal is to bring the bulb markers to a predefined point between the robot fingers. A piecewise linear visual motor model is estimated online and used to transform visually defined trajectory segments into joint motions. The bulb is screwed in using a predefined motion sequence. In the second task, the robot arm solves a kid's shape sorter puzzle. Here the 2 fixed cameras on the tripods are not moving. The puzzle pieces are picked up with a magnet. The needed movements fall into 2 classes: translatory long-range transportation moves and fine manipulation using both translations and rotations. For the translations, the first 3 arm joints are used, while for the fine manipulations both the arm and wrist are moved. Thus, a simpler 3-degree of freedom model is estimated for most movements. The full model only needs to be learned near the insertion point. During transportations, one feature is tracked in each camera. During fine manipulation, full object pose is controlled by tracking several corners. Once aligned, the piece is inserted. The estimated model is used here also, but now open loop, without visual feedback. This is how the task looks like on the trajectory planning level. Planned trajectories are compared with the actual movement, and the model is updated based on any discrepancy. When switching modes, the fine manipulation model is bootstrapped from the simpler transportation model. Trajectories are planned in stereo camera space using local visual models defined by the lines and corners found in the scene. These visual models are approximately Cartesian and thus define above and sideways. In summary, we have shown how to use uncalibrated visual surveying and visual space task planning to solve real-world manipulation tasks without needing any a priori camera, robot, or world calibration.
Full-scale mobile research robots. Real-time dynamic trajectory optimization with application to free-flying space robots. USA.
This video presents the first ever experimental demonstration of a real-time dynamic trajectory optimization system. Dynamic trajectory optimization is a powerful technique for robot motion planning that produces highly efficient trajectories, but has previously only been used in simulations and offline planning systems. In this video, the system is shown controlling a free-flying robot to intercept a moving target vehicle. The robot is propelled by 8 compressed air thrusters. Because of the expendable nature of the compressed air supply and the limited intercept workspace, the fuel and time efficiency of the planning system is critical. The real-time dynamic trajectory optimization system works by instructing the robot to start moving along a quickly generated but less efficient trajectory, and then, as the trajectory is optimized, improved sections are swapped in. In this manner, the robot is able to react immediately in response to the user's command, and is also able to switch over to improved trajectories as soon as they are produced. The real-time dynamic trajectory optimization system not only produces highly efficient trajectories, it is also able to react to unpredicted events because the constraint equations of the optimization system are modified in real time according to live sensor data. In this demonstration, the robot is able to react efficiently to unpredicted maneuvers made by the target vehicle. In summary, this work has enabled the powerful technique of dynamic trajectory optimization to be used for motion planning in a realistic environment where the state of the world is always somewhat unpredictable.
The Stanford Robotic Platforms, USA.
Autonomous parallel parking of a non-holonomic vehicle. France.
The research program Praxitel aims to develop a novel urban transportation system. It will be based on a fleet of electric cars capable of autonomous motion. Several experimental cars have been developed. Their manual driving has been supplemented with an automatic steering and velocity control. The cars are equipped with various sensors, including ultrasonic ones for collision avoidance. Experiments are carried out on a four-wheel vehicle with front-driven and steering wheels. After driving the car near to a parking area, the driver starts the automatic parking mode and leaves the vehicle. During the motion, sensor data about the environment is processed to avoid collisions with obstacles. A map of the local environment is built. The borders of the parking bay are localized. Given the space available within the bay, a decision to carry out a parallel parking maneuver is made. During the maneuver, the environment is monitored and any change is taken into account. The motion control procedure carries out an iterative localization planning execution cycle. The car moves backwards and forwards to obtain the required lateral displacement within the bay. The sensor data is processed and the current location of the car relative to the environment is computed. Because the car is not yet close enough to the curb, further iterative motions are executed. The vehicle stops when it reaches the proper location within the parking bay.
Local maps for reliable travels, France.
Consider the simple mission where the vehicle has to move from an initial location to a parking space. Certain adjustments must be made in order to achieve the mission with sufficient reliability. There can be mechanical defects, such as the use of casters when reverse motion is needed. Another defect is the lack of knowledge of the initial position, as well as the inaccuracy of its estimation, represented here by elliptic sets along the path. Finally, the map can be false, as here, where the planned parking place is not at its correct place. We use exteroceptive information provided by polarized sonars in order to compensate for disturbances by convenient closed-loop tasks. The mission is split into 3 paths, each one referenced to some local element. The first part of the movement is marked by blue-colored elements. We can see the stabilizing effect of the control. Next, there is a part marked by orange elements corresponding to a small corridor. Finally, the parking maneuver is carried out with reference to the elements, displayed in yellow, that define the parking space. We now see the real experiment that was displayed on the previous control screen. The cables leading from the robot are only used for power supply and for acquisition of data for display. Control is performed by an onboard computer using the VxWorks real-time kernel. In the last experiment, the parking place is no longer at its planned location, and the vehicle should take this into account. On the control screen, we see how this is interpreted by the robot when the local map changes. We see the discontinuity in the estimated position due to the fact that the new reference frame is not at the expected place with respect to the previous one. The stabilizing control law finally compensates for this and leads to a successful completion of the mission. This is the corresponding reality where we can see another type of disturbance due to the umbilical cord.
Robotic subsystem sensing technology. Development and experimentation with the Agile Eye. Canada.
The Agile Eye, a high-performance 3-degree of freedom camera orienting device, has been developed in the robotics laboratory at Laval University. The workspace and dynamic properties of the Agile Eye are superior to those of the human eye. The axis of the camera can be pointed within a cone of 140 degrees opening with plus or minus 30 degrees in torsion. An example trajectory is now shown in slow motion and at full speed. A dynamic model of the mechanism has been developed and implemented in the controller, which is based on a high-speed DSP. The dynamic model can be computed in real time at a servo rate of 500 Hz. This allows the Agile Eye to perform trajectories involving angular velocities of more than 1,000 degrees per second and angular accelerations of more than 20,000 degrees per second square with very small errors. The dynamic performances of the Agile Eye make it possible to move very rapidly from one orientation to another, which is a useful feature for many applications. A user interface has been developed for the planning of trajectories. The interface also allows the Agile Eye to be controlled manually by tracking the motion of the mouse. Experiments currently underway are focusing on the implementation of visual tracking algorithms.
Realization of enveloping grasp, Japan.
The wedge effect-based enveloping grasp is first demonstrated. This procedure is explained by the wireframe model, where the red and the white joints denote the compliant and the position control joints respectively. Detecting the table and the object is done by utilizing a joint torque sensor. In the grasping phase, a constant torque command is sent to each joint. the grasp system behaves as if a virtual spring were connected. The enveloping grasp can also be achieved even if there is more than one object. This grasp procedure is also available for a polygonal object. For the object whose cross-section is triangular, however, the wedge effect can no longer be expected. For such an object, the robot finger automatically switches into the rotating motion-based grasping procedure. By dual contact motions, the finger detects the object's width and the local slope. The goal of the active sensing is to detect the pushing point for rotation without any tactile sensor. To do this, one finger is traced over the object's surface until it detects the point where a normal force can generate a rotating moment. After detecting the pushing point, the finger rotates the object such that the fingertip can be inserted between the object and the table. Then, constant torque command is sent to each joint for the target grasp. In this experiment, we are placing various kinds of objects randomly. Of course, the robot finger does not know in advance what kind of object is tested. This particular experiment is for a quadrangular object. Because of the simple nature of the procedure, the finger first tries to utilize the wedge effect. This approach can effectively work for a cylindrical object. This cylindrical object is covered by a rubber coating so that we purposely increase the contact friction. Under such significant friction, the wedge effect-based approach does not work anymore because the slipping motion between the link surface and the object cannot be produced. To cope with this situation, we execute the lifting motion by rolling, as shown in this experiment. The robot finger adaptively switches its strategy into the most appropriate one based on the joint torque sensor information during the grasping task.
From Touch to Motion, Canada.
This video segment demonstrates our research in touch-driven robot manipulation. Our experimental system consists of a Puma 260 robot and a 16x16 array tactile sensor that covers an area of 1 inch squared. We have formulated a general framework called tactile servo, in which the state of a manipulation task is defined by the tactile image as the robot makes contact with its environment. Through sensor modeling, mapping is established between the sensor image space and the robot task space. In the first experiment, the task of edge following is performed. The tactile sensor is mounted on a planar end effector. Both the location and orientation of the edge, as well as the contact force, are determined. Differential motion commands are then derived to guide the robot to move along the edge while maintaining a desired contact force. In the second demonstration, a similar task is performed. The spherical body of a light bulb is explored by the robot end effector. In both cases, a constant contact force is maintained, and the shape of the object being explored is reconstructed. Our tactile servo framework has also been applied to object manipulation tasks. Shown here is one example where the robot manipulator pushes a rolling pin back and forth on a pen tilt table. The robot determines the state of contact from the tactile sensor while the rolling pin is perturbed by random motion of the pen tilt table. Even when disturbance occurs in multiple directions, stable and responsive performance is achieved. We're currently extending the tactile servo framework to the control of multiple fingered hands. In addition, we're investigating the integration of visual servo with tactile servo to perform tasks for which either sensing modality by itself is insufficient.
force sensor for soft grasping with optocouplers as sensing elements. Yugoslavia.
New soft textile sensors using reflection optocouplers as the basic sensing elements are developed. Two pairs of sensors surround the object and detect its movement caused by the external forces. Complete sensor consists of three main parts. Upper rigid plate carries soft rubber on one side and white reflective surfaces on the other. There is the sensor's elastic body made of silicon rubber on the lower rigid plate. On a printed circuit board are located the optocouplers and the other electronic components. If force is applied, elastic body deforms. Sensing elements measure its deformation in normal and tangential direction. Two optocouplers are mounted near the ends of the sensor, measuring the object inclination. One optocoupler, orthogonally mounted in the middle of the sensor, is sensitive to axial deformation. Using information from all sensors simultaneously, intensity and direction of external force can be determined. In this experiment, robot arm retreats, tending to eliminate the excess external force acting on the object. Now, robot tends to keep the force constant and to ensure bilateral manipulation of the pencil with the human. In the presence of excess force, it retreats. If the external force decreases, the gripper advances. Measuring intensity and direction of the reaction forces enables to keep the pressure on the pen tip constant, as demonstrated in the next experiment. Robot draws a handwritten figure on a curved, unknown, and arbitrarily inclined surface.
Experiments of robotic assembly instructed by situated natural language. Germany.
When solving complex assembly tasks in cooperation with a human partner, easy instructability of robotic systems becomes a key requirement. To make better profit of the ways humans communicate, we incorporate aspects of natural language into robot control. Our natural language-based approach is demonstrated first with the Cody Virtual Constructor, a simulation system for interactive assembly tasks in virtual environments. Sample interactions are: insert the bolt into the short bar, attach the yellow bolt to the bottom of the block, show the elevator control. The last example demonstrates that the system can also understand references to constructed assemblies. To implement the real assembly, a robotic system with two Puma 260 manipulators has been developed. A force torque sensor and a hand camera are integrated in each pneumatic jaw gripper. An overhead camera supervises the complete assembly scenario. The construction parts have been placed randomly on the table, and the overhead camera takes an image of them. An image processing system recognizes the parts and computes their approximate locations. The instructor now types in "grasp a bolt." The whole grasping operation is supervised by the self-viewing hand camera, which has the gripper in view. The exact positioning of the gripper over the part to be grasped can be achieved by the visual control algorithm. The next instruction is grasp a bar and insert the bolt into the bar. Uncertainties like slippage and position inaccuracy can occur during such an insertion operation. Therefore, we apply the sensor-based control to ensure this operation is robustly performed. Another instruction, grasp a block. Now, screw the bolt into the block nut. A learning approach can optimize the forces required for the screwing operation. Our experiments show that the use of natural language instructions is a promising way to make the interaction between humans and robotic systems both more flexible and more intuitive.
Micro-robots. Building a soccer robot system for Myrosat 96, Korea.
We are now developing soccer robots which provide a common test bench to various multi-agent systems and tested for mobile robots. Myro and Sortie mainly consist of two parts, the robots and vision system. For the aim of autonomous cooperating multi-robot system, each robot equipped with onboard CPU, sensors, and rechargeable batteries. The onboard 16-bit controller Intel 8OC196KC manages and processes the information either from the onboard sensors or from the external vision system through the host computer and gives commands to the motors. 8 infrared sensors for perceiving obstacles around can detect the distance in 3 different steps: close, far, and very far. They are deliberately designed so as not to be sensitive to the external light condition. The other 8 infrared sensors under the body detect white lines on the field so that the robot corrects its accumulated position and orientation errors. The vision system can catch objects on the field and process to get their positions with 1 centimeter error about 10 times a second. It broadcasts this information to the robots. The robot has 4 basic behaviors: movement, obstacle avoidance, shooting, blocking, and uses them according to the decision of a high-level controller. Movement behavior shows 3 motions like move forward, turn, and backward when the desired position is given from the high-level controller. The side sensors are for detecting walls and other robots except the ball. Obstacle avoidance behavior must be included to meet the game rule. Shooting behavior is a special behavior for Myro and Sortie because they don't have a shooting mechanism. To shoot the ball toward the goal or some places, the robots push the ball using their body. Blocking behavior is moving toward a place in the line of opponent robot's attack to block the ball moving toward the goal. Myro and Sortie's basic strategy is zone defense. Each robot has its defense area and reacts only according to the ball position. The robots can play soccer through these basic behaviors and strategy. This film shows play of Sortie, the team with blue patches, and Myrosat 96, the Micro World Cup soccer tournament held at KAIST, Korea during November 9th through 12th, 1996. Where Sortie and Myro took the second and first places respectively.
Heat, a short-lived navigational marker. Australia.
Many insects use short-lived odor markings to help them to function efficiently. A familiar example is the foraging ant that lays an odor trail to mark the path between a source of food and its nest. Worker ants follow this trail to transport the food back to their nest. A family of inexpensive robots has been developed at Monash University to investigate the practical problems and potential uses of similar short-lived markings. This particular robot carries a pyroelectric sensor as well as proximity sensing whiskers. This robot is programmed to search for and then follow a heat trail, while avoiding walls and other fixed obstacles. The heat trail has been laid by a larger robot carrying a 70-watt quartz halogen bulb. When heat is detected, the robot turns to follow the trail. Because the robot's pyroelectric sensor is only sensitive to heat changes, the robot follows the trail by repeatedly moving forward and then rotating to detect the edge of the trail. If a temporary obstruction blocks the trail, the robot is programmed to wait a length of time proportional to the time it has been following the trail. In this segment, we see Robot 3, which has been following the trail for some time, being blocked by Robot 4. When Robot 4 gets out of the way, Robot 3 continues tracking the trail. If the obstacle does not move within the timeout time, the robot gives up and looks elsewhere for a trail. While following a heat trail, the robot meets an immovable obstacle blocking its path. After timing out, the robot backs away from the obstacle and goes in search of another heat trail. It is hoped that by using short-lived marking schemes, such as heat or odor trails, relatively simple robots will be helped to perform useful tasks. Potential applications are seen as recruiting specialist robots from a number of different robots circulating in the work area, indicating temporary exclusion zones within the robot work area, and marking paths for other robots to follow.
Multi-robot box pushing, Canada.
Research in collective robotics at the University of Alberta has focused on the reactive control of decentralized systems of mobile robots. The objective in the transport task is to locate a brightly lit box and move it to a goal location located at the left side of the screen. The box is weighted such that at least 2 robots are needed to accomplish the task. The goal position is indicated with an overhead spotlight placed at one corner of the lab environment. The robots do not explicitly communicate and are not centrally controlled. The robots also do not differentiate between objects and other robots. 6 robots starting from a random initial position must locate the box using 2 forward-pointing light sensors. Once a box side is located, the robot determines if the box is between the robot and the goal using an upward-pointing goal sensor and either pushes or repositions itself on the box. Repositioning can and often does cause the robot to lose sight of the box, since the field of view of the box sensors are not omnidirectional. This results in the robot having to relocate the box and find a box side and determine the goal location. The box can be transported between different goal positions by sequencing the goal indicators. In this demonstration, a round box was first moved from the center of the room to the goal at the right of the screen. The task is divided into 3 steps, with a reactive controller designed for each step. Transitions between steps are specified as locally sensed perceptual cues, a simple concatenation of binary sensor values. The first step controller is designed to find the box while executing a random walk. Once the box is detected, the second step controller moves the robot towards the box until contact is made, which causes transition to the last step. The final step controller determines the box direction and causes the robot to either reposition itself on the box side or begin pushing. The approach demonstrates simple cooperative behavior using reactive control without need of an explicit mechanism of coordination.
Control dynamics and kinematics. An ultra-high-speed robot, Falcon, using parallel wire drive system. Japan.
An ultra-high-speed robot, Falcon, using parallel wire drive system. For high-speed motion, we have proposed an ultra-high-speed robot, Falcon, based on a wire-driven parallel manipulation system. The parallel wire drive system utilizes wires instead of links to control an object. Wires are employed to extremely reduce mass and inertia for achieving ultra-high-speed operations. However, since wires generate only tension, or wires have one-directional actuation, redundant actuating mechanism is necessary. Falcon means fast load conveyance, and Falcon 7, which has 7 wires to realize 6 DOF motions. Each wire is rolled by a pulley which is connected to a DC servo motor. The dimensions of the frame are 1.4 times 1.4 times 1.2 meter. The wires are made of steel, 0.5 millimeter in diameter. The pulleys and gears are made of hard plastic and a gear ratio of 5:1. The rod is made of duralumin and has a length of 1 meter and a mass of 150 grams. Rotary encoders are used to sense the length of each wire. Each DC motor is driven by a simple PD feedback control law on the wire length. In high-speed motions, vibration comes up as a crucial problem. To eliminate vibration, internal force which is generated by redundant actuation is effectively utilized. As a result, vibration does not occur in high-speed motion of the proposed robot. Even if the servo motors has 60 watts capacity, the peak acceleration achieves over 100 G and maximum velocity achieves 13 meters per second. The adept motion is a trajectory of moving upward 25 mm, sliding 300 mm, and downward 25 mm back and forth. Falcon 7 achieves 0.37 seconds per cycle of the adept motion. Because of high-speed motion, after-image phenomenon occurs. Many circles can be seen in this experiment.
Control of a flexible micro-macro manipulator, USA. In teleoperation, it is often required for a robotic manipulator to perform a fine motion in a large workspace. A micro-manipulator attached to a macro robot system has been proposed to meet such needs. To demonstrate vibration and contact control, we created a test bed of an industrial hydraulic manipulator as a micro-manipulator and a 12-foot-long link as a macro-manipulator. The motion of the micro-manipulator with a conventional PD controller can easily excite the macro-manipulator. These structural vibrations can last more than a minute and have detrimental effects on safety and efficiency. However, with inertial force active damping control, the micro-manipulator counteracts the structural vibration using strain gauge feedback at the base while it follows desired positions. Both horizontal and vertical vibration damp out in less than 2 seconds. If an external impulse is applied at the tip, the vibration in the vertical and horizontal directions can also last more than 1 minute. Again, by applying inertial force active damping control, the controller can damp out the vibrations in less than 2 seconds. The micro-manipulator is teleoperated by a spaceball input. When an arbitrary path is applied by the operator, the manipulator oscillates and cannot follow the exact path. With inertial force active damping again activated, the manipulator follows the exact path without the vibrations.
In another example, a digital force-torque sensor was attached at the wrist of the micromanipulator, and a force controller was implemented to the manipulator. As a force is applied to the sensor, the hydraulic manipulator moves accordingly. When a force-controlled manipulator makes a contact with a very rigid surface, it is well known that the contact instability occurs. The frequency of the limit cycle depends on the link compliance and force controller gains. Again, with inertial force active damping control, the manipulator can make a smooth transition to a contact without chattering by dissipating impact energy. To demonstrate that the contact force is being regulated, a paper cup was used. Using the force-torque sensor at the wrist, a small force in the horizontal direction is controlled. And as we can see, the cup is not dropping or being crushed. Holding a cup against a wall is a relatively simple task since the cup is very flexible. This time we experimented with something not so compliant, a fragile egg. Again, the manipulator is force-controlled in the horizontal direction. The manipulator contacts the egg and regulates the holding force to be about 1.5 pounds. Any overshoot or chatter of the force control will break the egg. Here, a hydraulic manipulator system with an 18-foot-long reach running at 3,000 psi is holding an egg against the wall. To further demonstrate the system, an operator performs a teleoperation task of inserting a peg in a hole with visual information provided by a video camera. With the proposed controller, an operator could insert a peg in a very tight hole with a clearance of 10/1000ths of an inch. The force control makes fine alignment adjustments that visual information cannot provide. The inertial force active damping controller eliminates the vibration before and after the contact. Using an industrial manipulator testbed, the vibration and contact control of a flexible manipulator is demonstrated. With the proposed control, the micro-macro manipulator will be able to perform a fine motion in a large workspace accurately, efficiently, and safely.
Reconfigurable Modular Manipulator System Project, USA.
In the Advanced Manipulators Laboratory at the Robotics Institute of Carnegie Mellon University, we have developed a reconfigurable modular manipulator system, or RMMS. The system currently consists of 5 modules that can be assembled and reassembled into multiple configurations of manipulators, each with different kinematic and dynamic capabilities. The goal of the project is to develop a system that allows the user to rapidly create and program a manipulator which is custom-tailored for a given task. Each of the modules of the RMMS is a self-contained unit which includes a microcontroller, power amplifier, sensor interface, and a communication interface. An integrated quick coupling connector allows the modules to be assembled and disassembled without using any tools. A secure mechanical connection, as well as a pneumatic and electronic connection, is achieved by turning a locking collar hand tight. The connectors also contain an LED and photodetectors to determine automatically in which of the 8 possible orientations an RMMS module has been mounted with respect to the previous module. To evaluate new manipulator configurations quickly and safely, we have built an RMMS simulator using Telegrip simulation software. The user can build an RMMS configuration interactively by selecting modules from a database and mounting the modules in the appropriate orientation. The simulation runs on a Silicon Graphics workstation which is connected to the real-time control hardware. This allows us to simulate a task while running the control software on the real-time processor used to control the physical RMMS. When the manipulator is powered up, all the modules connect to a local area network. Over this network, a VME-based host computer retrieves the serial number and orientation of each of the modules. The host computer then automatically builds kinematic and dynamic models that are used to compute the inverse kinematics and the feed-forward torques. Individual joint PID controllers run locally on the microcontrollers in each of the joint modules. They receive the desired joint positions and gravity compensation torques via the local area network. The same task can be performed using a different RMMS configuration without the need to alter the original program. This reconfigurability allows the RMMS to address a much larger range of tasks than traditional fixed configuration manipulators. To determine the RMMS configuration that is optimally suited to perform a given task, we have developed task-based design software. This software uses an agent-based implementation of a genetic algorithm to search for an RMMS configuration that satisfies all the task requirements with minimal energy consumption.
Follow the leader control of hyper-redundant serpentine truss manipulator prototype hardware, USA.
The Payload Inspection and Processing System is under development for pre-launch inspection of the Shuttle Bay at NASA Kennedy Space Center. This videotape demonstrates follow-the-leader control of prototype hardware for snake-like obstacle avoidance. Given an obstacle-free trajectory for the manipulator tip, the follow-the-leader algorithm ensures whole-arm collision avoidance by forcing each link to follow the tip. The system is programmed offline by teleoperation. It also accepts trajectories from path planners. Offline computer graphics software is used to validate motion prior to operating the hardware. Hardware includes a blue prototype serpentine truss manipulator with 18 degrees of freedom, a white shuttle payload pallet, and a gold mock-up payload for the next Hubble servicing mission scheduled to fly on STS-82. The manipulator tip carries a camera for remote inspection. 4 collision-free trajectories were developed offline, representative of inspection locations for the STS-82 payload. Since follow-the-leader trajectories require minutes to execute, one time-lapse trajectory is demonstrated. The inspection goal is represented by the NASA logo. The system is capable of inspecting locations which are dangerous or inaccessible to humans. At the end of the trajectory, camera pan, tilt, and zoom may be used to better view the inspection goal. The manipulator is retracted by reversing the commands. Follow-the-leader control has been successfully demonstrated. The prototype hardware has yielded design and control lessons which will be used to develop the launchpad hardware.
Planar manipulation on a conveyor with a one-joint robot. USA and Japan.
Our work explores a simple and flexible parts feeding method for industrial automation. We use just one joint to manipulate the 3 degrees of freedom of a planar part on a conveyor belt. We refer to this approach as one joint over conveyor, or one jock for short. In this implementation, we use one joint of an adept robot to rotate a fence over the conveyor. A singulated part drifts down the conveyor and comes to rest against the fence. It is moved from this initial configuration to a specified goal configuration using pushing motions of the fence punctuated by drift along the conveyor. We demonstrate that it is possible to move an arbitrary polygonal part from a broad range of initial configurations to a specific goal configuration, and that it is possible to choose that goal configuration from a broad range of possible goals. We demonstrate 3 plans, viewed from above, to transfer a triangular part to this goal configuration from 3 different initial configurations. Our first example is a single-stage plan. It consists of a turn, which rotates the part to change its resting edge, and at the same time changes its position along the fence. We use the mechanics of pushing a part to identify the types of pushes which guarantee a valid plan. We use a nonlinear programming formulation to determine the parameters of this plan. The remainder of the tape is shown at approximately double speed. Our second example only requires a change in the position of the part along the fence. This is accomplished by a series of jogs. Our third example is a 2-stage plan. It consists of 2 turns, which rotate the part to the correct resting edge, and at the same time achieve the correct position along the fence. Our future goals include speeding up execution of the plans and creating plans that are more robust to variations in part shape.
Non-prehensile robotic manipulation, USA.
We're studying manipulation by simple robots without grasping. 2 examples are quasi-static pushing and dynamic manipulation. By not grasping, simple robots can exploit frictional and dynamic forces to perform complex tasks. Pushing allows a robot to manipulate parts which are difficult to grasp and carry. To plan pushing operations, we specify the part's shape, center of mass, a set of pushing edges, and the friction coefficient. The computer automatically identifies stable pushing motions. These stable pushes are used by a non-holonomic path planner to find the pushing path. The plan is then downloaded to an adept robot. Here a square is rotated 180 degrees in a tight space by pushing on 2 edges. There is no feedback. The mechanics of stable pushing make the plan robust. Pushing may be especially useful for mobile robots manipulating boxes. By exploiting dynamic forces, a 1-joint robot can control 3 degrees of freedom of a part. We have developed a motion planner to solve a variety of dynamic tasks while satisfying friction constraints. The following tasks were planned and executed automatically. Here the arm snatches a block from a table without using a gripper by accelerating into it. If we slow the planned trajectory to 2/3 speed, or increase it to 3/2 speed, the snatch fails. Here we reorient the part on the arm by throwing and catching. In this example, the robot first snatches the block and then reorients it by throwing and catching. Here the arm rolls an object on its surface. Note the wind-up before the first roll. By rolling before throwing, we can throw a part with an angular velocity different than the arms. Here the block rotates a 1/4 revolution clockwise. Here the block rotates a 1/2 revolution clockwise. Finally, the block rotates a 1/4 revolution while changing its position. These examples of graspless manipulation show how robots can use frictional and dynamic forces to advantage.
Control of a 3 degree of freedom planar under-actuated manipulator. Japan.
control of a 3 degree of freedom planar under-actuated manipulator is investigated. The manipulator has 2 active joints and 1 passive joint. The dynamic constraint of the free link is a second-order non-holonomic constraint. The objective of the control is to manipulate the position and orientation of the free link using the non-holonomic constraint. The link can translate without rotation when the joint is accelerated towards the center of mass. Nonlinear feedback control stabilizes the free link to the trajectory. The motion of the center of percussion of the link is considered, and an exact linearization is applied to the system. The center of percussion of the link stays still if the joint follows a circular trajectory around it. The link can rotate without translation. This trajectory is also stabilized by feedback control. Without feedback control, each trajectory is not stable. The link deviates from the trajectory as shown. Combining these trajectory segments, the link can be positioned to any configuration. Positioning of the link is achieved by a rotation, translation, and rotation. The link translates, rotates, and then translates to the desired configuration in this case. This method can be useful in building lightweight, low-cost manipulators and in fault tolerance of manipulator control.
Telemanipulation. Task lines and motion guide demonstrations, USA.
Researchers at Jet Propulsion Laboratory have recently developed new telerobotics technologies called task lines and motion guides. These technologies are demonstrated here with 2 robots being controlled from an operator control station in a remote building. A motion guide is a graphical representation of the path a robot will follow, but with the important distinction that the path is teleoperated rather than the robot. Here, the operator modifies the position of the motion guide in simulation using a hand controller. The robot is constrained to stay on the motion guide. The motion guide is teleoperated into a position where the robot will not collide with the truss during the motion, and so that the view from the gripper camera at the end of the motion will be of a bottle hidden within the truss. The simulated view from the gripper camera is shown in the upper left graphics image. The robot is then driven down the motion guide with a constant velocity command. The robot follows the motion guide into the truss, and at the end of the motion, the bottle comes into view. A second motion guide is used to control an 11 degree of freedom serpentine manipulator, inspecting the inside of a cavity. In this case, the operator drives the robot down the motion guide by pushing on a space ball. As long as the operator is pushing forward on the space ball, the robot moves forward along the motion guide. If the operator releases the space ball, then the robot stops. As the robot enters the opening, the inside of the cavity can be seen from the camera attached to the end of the robot. The operator pulls back on the space ball to command the robot to move backward along the motion guide. The task lines technology is used here in a multi-sensor inspection task. A task line is a motion guide with graphical icons attached to it. These icons indicate subtasks to execute. Here, a camera icon indicates to execute an automated visual inspection subtask. A thermometer icon indicates to begin temperature scanning, and a cloud icon indicates to begin gas scanning. When the operator initiates the scan, the robot follows the motion guide. When the robot arrives at a location which has one or more icons, then the subtasks associated with the icons are executed. When the subtasks are complete, then a camera is automatically pointed at the next position which has an icon. If an automated visual inspection subtask detects a flaw, then the camera icon at that location is turned red. Otherwise, it is turned green. If a temperature anomaly is detected, then a red thermometer icon is placed at the temperature anomaly location.
Real-time collision avoidance for dexterous 7 degree of freedom arms. USA.
The NASA Ranger telerobotic flight experiment, led by the University of Maryland, is aimed at the development and demonstration of robotics technologies for executing manipulation tasks in space. JPL is augmenting the Ranger baseline system by providing automated obstacle detection and collision avoidance capabilities. The fundamental problem, which is addressed by our Ranger augmentation, is that of avoiding collisions between a dexterous robotic arm and objects in the environment, such as other arms, the base, and the task board. Perturbations to arm trajectories for collision avoidance must be made gradually in order to avoid sudden jerks, which can damage the arm or lead to undesirable oscillations. In our approach, we surround each potential obstacle with a safety zone. Collision avoidance is accomplished with a new method developed at JPL that uses virtual spring and damper forces to repel intrusions into this zone. Because Ranger has no proximity sensors, simplified geometric models of the arms and obstacles are used to calculate obstacle distances for computing the virtual intrusion forces in real time. In 1996, JPL integrated the collision avoidance method into a real-time arm control system and tested its capabilities experimentally with dexterous 7 degree of freedom arms. The experimental facility, the JPL Remote Surface Inspection Laboratory, includes a 1/3 scale partial mock-up of the International Space Station, 2 Robotics Research Corporation dexterous 7 degree of freedom arms, a VxWorks VME arm control computer into which the obstacle detection and collision avoidance software is integrated, and an operator control station with video displays, joysticks, and a graphic workstation for simulations and user interface displays. In this experiment, real-time collision avoidance allows a robotic arm to safely navigate within a truss opening. With avoidance turned off, the commanded trajectory follows a diamond-shaped pattern with the end effector almost touching each of the sides of the truss opening. When avoidance is turned on, the end effector stops its motion toward the sides of the truss at a safe distance, while continuing its movement in directions not affected by the virtual intrusion forces. This experiment illustrates orientation perturbation for avoidance of a near collision between the wrist of the right arm and the top edge of a rectangular box in the workspace. If the obstacle is closer to the wrist than a preset distance, the end effector orientation is perturbed automatically to rotate the wrist away from the obstacle while maintaining the commanded position trajectory. In this experiment, we demonstrate reconfiguration of the arm to avoid an impending collision. When the elbow comes close to an obstacle, in this case the left arm, then the dexterity of the arm allows the collision avoidance software to rotate the elbow away from the obstacle without perturbing the commanded position and orientation of the end effector. This experiment illustrates position perturbation for avoidance of a near collision between the right arm and the base pedestal of the left arm. The right arm is commanded to execute a trajectory which, with collision avoidance turned off, takes it within a centimeter of the base of the left arm. When collision avoidance is turned on and the arm is commanded to move along the same trajectory as before, the end effector position is smoothly perturbed to automatically maintain a user-specified distance from the left arm base. The collision avoidance capability is effective not only with static obstacles, but also with moving arms, including itself. In this experiment, we demonstrate the end effector maintaining a safe distance from the upper arm link of the same arm to avoid self-collision. Position, orientation, and elbow collision avoidance may be activated or deactivated in any combination and apply equally to autonomous sequence execution and to teleoperation. In this experiment, the user is teleoperating the robotic arm within the truss opening. As soon as the end effector gets close to a side of the opening, a repulsive force is generated in the software which impedes the teleoperation command and inhibits motion toward the truss. The real-time online nature of the avoidance capability allows teleoperation with no prior trajectory planning or simulation. These experiments have clearly demonstrated the effectiveness of the JPL-developed capabilities for real-time collision avoidance of dexterous 7-degree of freedom arms.
The 5-bar linkage force reflecting interface for virtual reality system, Canada.
At the University of Waterloo, a 5-bar linkage haptic interface has been designed as part of an inexpensive virtual reality workstation. This input device allows a user to touch virtual objects in the real world. This robot has been designed to be dynamically decoupled and gravity balanced in all configurations. This allows all gearing mechanisms to be eliminated. Inertial effects are minimized by making the robot links very lightweight. Force controllers have been utilized to simulate free motion, where the already small inertia of the robot is made to appear even smaller. Implicit force controllers can also be used to simulate touching a virtual wall. Here, the robot is shown moving into a virtual surface. This is the surface that the user would feel using this haptic interface. When an implicit force controller is used and the stiffness of the virtual wall is increased, instability can result when the user attempts to touch the wall with a constant force. Recently developed techniques have shown that the instability can be reduced to a great extent by the use of a switching control strategy. Using a Pentium computer, it is possible to incorporate both the graphics interface and the haptic interface on the same platform. Moving the robot moves the cursor on the screen. When the cursor strikes the virtual object, the user will feel it. Future research will examine more sophisticated virtual objects and force control strategies.
Computer-aided design and simulation. An interactive assembly planning system, USA.
This video introduces and briefly demonstrates Archimedes, an interactive assembly analysis program under development at Sandia National Laboratories. A user of Archimedes begins a typical session by selecting the CAD model of an assembly to analyze. The program loads the models of the parts and automatically finds part-part contacts. Once the product model is loaded, Archimedes can produce an initial assembly plan. The planner automatically determines a possible order of assembly for the product, proceeding in reverse for reasons of efficiency. Assembly motions and subassemblies are generated based on the part contacts and then checked for collisions. For this product, a first assembly plan is found in less than a minute. The user can immediately view an animation of the plan graphically from any angle using simple VCR-like buttons to control the animation. Often, the first plan Archimedes chooses does not satisfy known process constraints. For example, in this product, the drive gears should be placed on the motors before assembly with the plate, and the mounting screws must fasten the motors to the plate immediately after the motors are placed. The user guides Archimedes in its choice of a plan by placing constraints on the allowable plans. For instance, to address the first problem, the user can add a require subassembly constraint, selecting the gear and motor as the parts of the subassembly. For the mounting screw problem, the user can add a require fastener constraint, specifying the motor and plate as the parts fastened, and the 4 screws as the fasteners. After adding any other constraints desired, a new plan is requested. By reusing computation from the first run, Archimedes finds a plan that satisfies the new set of constraints within seconds. The speed of replanning enables a plan, animate, constrain, replan cycle that is highly effective for constraint discovery and planning. Constraints in Archimedes are implemented as filters on assembly operations. This standard architecture supports over 20 constraint types in the current system. If desired, plans more suitable for automated assembly can be generated by using reorientations and only vertical insertions. Archimedes has been tested on tens of complex products from sources in government and industry. The interactive constraint system demonstrated here has proved to be highly effective in these experiments.
High-pair, interactive mechanism simulation, validation, and tolerancing using configuration spaces, USA and Israel.
High-pair, interactive design of mechanisms with multiple contacts, by Alicia Sachs and Leo Jaskowitz. Mechanisms perform their functions by transforming motions through part contacts. In many modern mechanisms, different part features interact at different stages of the work cycle. For example, the shutter mechanism of this camera exhibits multiple contacts between its 10 moving parts. To take a picture, the user first winds the advance wheel, which advances the film by 1 frame and loads the shutter release. The user then presses the shutter release, which opens the curtain and exposes the film. Notice how the part contacts change during the work cycle. Multiple contact mechanisms are more difficult to design than are mechanisms with fixed contacts, such as linkages and cams. The designer needs to identify which part features interact at each stage of the work cycle and to validate each interaction. Current computer-aided design programs provide little support for multiple contacts. The designer must perform many difficult computations by hand. High-pair is the first computer-aided design program that automates these computations. It helps designers analyze part interactions, identify design flaws, perform tolerance analysis, and modify designs. The computations take only a few seconds for mechanisms with thousands of part features, such as the camera. High-pair computes the kinematic function of a mechanism from a specification of its part shapes, relative positions, and degrees of freedom. It constructs a geometric representation of the kinematic function called a configuration space. It supports design tasks by manipulating the configuration space. The configuration space of a mechanism is a geometric representation of the positions and orientations of its parts. This is the configuration space of the Geneva mechanism. The horizontal axis shows the angular displacement of the driver. The vertical axis shows the angular displacement of the wheel. The white region represents free configurations. The gray region represents overlapping configurations. The black curves that bound the free space represent configurations where the parts touch. They encode the contact relations between the wheel. High-pair supports kinematic tolerance analysis of multiple contact mechanisms, such as this 26-parameter model of the Geneva mechanism. High-pair computes the variation in the kinematic function directly from the shape and position tolerances of the parts. We model kinematic variation by generalizing configuration space to toleranced parts. Here we see a detail of the generalized configuration space of the Geneva mechanism. The curves that form the contact space are parameterized by the tolerance parameters. As the parameters vary around their nominal values, the contact curves vary in a band around the nominal curves, which we call the contact zone.
Industrial applications. Advances in Agile Manufacturing, USA.
This video describes the design of an agile manufacturing work cell for performing light mechanical assembly. In this context, agility refers to the capability of manufacturing a wide range of products based on quickly changing customer needs. Both the hardware and software components of this work cell have therefore been designed to accommodate the rapid introduction of new assemblies and rapid changeover between existing products. Assembly operations are performed by a pair of Adept 550 robots, and a conveyor system is used to transfer fully and partially completed assemblies to and from the Adept 550s. Parts are presented using generic flexible feeders, which are designed to work for a wide variety of parts. The relatively primitive Adept robot controller has been augmented by an innovative control system. This allows the use of object-oriented programming and advanced programming tools, which in turn permit software to be modified quickly and efficiently. To expedite software maintenance, a graphical work cell simulation was developed. Control programs can be tested on this virtual work cell where software errors can be safely detected. This facilitates changeover by reducing work cell downtime and the risk of equipment damage. In order to grasp a wide variety of objects, a set of quick tool changers and modular grippers are used. Multiple grippers are typically mounted onto rotary wrists, thus reducing the number of tool change operations needed. Since parts must sometimes be fed in orientations that are unsuitable for assembly, a light rotary jaw gripper has been developed. This allows parts to be rotated into more desirable assembly orientations. In addition, this project is exploring a methodology for the automatic design and fabrication of multi-purpose robot gripper fingers based on CAD descriptions of the parts to be grasped. The system would use rapid prototyping technology to construct fingers out of rigid plastic sheets. This approach would facilitate the concurrent design of robotic grippers and product components. Specialized hardware is required for assembly tasks which cannot be easily performed by the robots. This hardware is fixed onto modular assembly tables that are easily exchangeable, allowing the work cell to easily switch between products. The modular tables are outfitted with a set of precisely positioned registration points, which the machine vision system uses to quickly register the work tables into the robot's world coordinate system. This eliminates the tedium of reteaching assembly hardware locations. The same approach is also used to register incoming conveyor pallets. In summary, this research demonstrates the importance of an integrated approach to the design of an agile manufacturing system. Both hardware and software components must be designed for rapid changeover if agility in manufacturing is to be achieved.
A Robertuator-based structure climbing inspection robot, USA.
Welcome to the Intelligent Robotics Laboratory at Vanderbilt University, where you will see our progress on the development of Robin. Robin is intended to be a vehicle for robotic inspection of man-made infrastructure, such as bridges, planes, buildings, and dams. Robin consists of two vacuum fixtures, or feet as we call them, connected by an articulated 4-degree of freedom mechanism. The motion of Robin comes from strong, lightweight pneumatic actuators called Robotuators. In the future, we plan to add sensors and cameras to Robin that allow the vehicle to inspect a structure, but for now we're just concentrating on basic locomotion and control of the robot. Here you see the power-up sequence where the Robotuators are filled with air and vacuum pumps are activated in preparation for walking. Low-level control functions are performed by a network of onboard microcontrollers, while sequencing of the walking motion is handled by an off-board host computer. Power is carried to the robot via a tether that also carries a serial communication link to the host computer. Walking is achieved by a sequence of extend and contract behaviors that move the robot along, much like an inchworm. Foot-orienting behaviors and vacuum control are triggered by optical proximity sensors on the robot's feet. Next, you will see a detail of Robin's vacuum fixtures. The fixtures have 5 suction cups, powered by a Venturi vacuum pump. Currently there is no feedback of vacuum, but we plan to add this feature soon. You can also see the optical proximity sensors that are out on the edges of the feet. Finally, we will show one of our first tests with Robin climbing a vertical surface. Here you can see the flexibility in the spring-like actuators, as evidenced in the oscillations of robot motion. The lightweight valves used by Robin have very low control bandwidth, and it is difficult to damp out oscillations with this control system. Although the current prototype is still under development, we hope that this video shows our progress toward a robotic vehicle that may someday become a tool for robotic inspection, carrying sensors onto bridges, planes, buildings, or dams, so that they can save the human inspectors the walk. For more information about this project, please contact us at the Intelligent Robotics Laboratory of Vanderbilt University. Thank you.
Ursula, a mobile robot for reactor vessel ultrasonic inspection. USA.
For nearly 20 years, the nuclear industry has used large manipulators to perform reactor vessel ultrasonic examinations. To help reduce examination time and simplify service operations, Framatome Technologies has developed the Ursula robot. Ursula incorporates a 6 degree of freedom arm mounted to a foundation equipped with 3 suction cups. High-velocity water is forced through the Venturi nozzle to produce attachment forces that exceed 300 pounds for each suction cup. In addition, Ursula is tethered in the unlikely event of suction failure. A waterproof housing protects Ursula's electronics. Onboard controls minimize cable requirements to connect Ursula with the surface. The robot scan location must be known in vessel space. The vessel space positioning system aims a centrally mounted laser at the desired location. Ursula is then moved to place the photosensitive target close to the laser dot. The laser then searches a small area to locate the center of the photosensitive target. Tests have shown this system to be accurate within 1 centimeter. Cables and support hardware can be staged prior to critical path vessel activity. Ursula may be lifted from the rack, transferred from the lifting crane to the safety tether, and lowered into the vessel. Nozzle scans require Ursula's most complex arm motions. All joints must move in a coordinated path to produce the desired rectilinear scan pattern on the nozzle surface. The compliant UT head absorbs slight bumps and misalignments of the robot with the nozzle axis. Each transducer slide floats over 1 inch from the nominally compressed position. The IEEE code requires periodic calibration checks. Ursula's onboard calibration blocks permit UT calibration checks with minimal interruption of vessel scanning. Ursula's compact design enables 2 robots to simultaneously scan and examine the reactor vessel in approximately 60% of the time required by 1 robot. 2 robots also ensure completion of the examination on or close to the target schedule. If 1 robot must be removed for repair, the other can continue to scan. Ursula continues to set new records for vessel examinations. Typical target times for IEEE Code Appendix 8 examinations using 2 Ursulas are less than 4 critical path days.
Advanced manipulation for deep underwater sampling. United Kingdom.
The current generation of robots used for remote operations in the ocean have crude grippers with no contact sensing. Amadeus is a collaborative European project developing a dexterous underwater grasping system using elephant's trunk flexible actuators for fingers. The development comprises the gripper mechanism, force and slip contact sensing, coordinated finger force and position control, supervisory grasp planning, and a graphical user interface. The gripper fingers use an elephant's trunk flexible actuator comprising 3 phosphor bronze bellows. The bellows are mechanically linked and filled with hydraulic fluid. Controlled pressure variations in each bellow create bending moments, causing the finger to move with 3 degrees of freedom. For additional movement, a hydraulic knuckle mechanism is incorporated into each finger. With 40 degrees of angular rotation, objects between 10 and 150 millimeters can be grasped. The finger design is inherently pressure compensated for use at depth and has natural passive compliance for robustness. At each fingertip, force and slip contact sensors are embedded within a silicon elastomer. The sensors are mounted on an aluminium skeleton with an O-ring sealed 50-way push-fit connector. To minimize changing ambient pressure effects, force sensing uses strain gauges arranged on the skeleton. Redundancy allows sensor fusion to better estimate force magnitude and orientation. Slip sensing uses a PVDF piezoelectric strip embedded above the skeleton. Slipping vibrations are transmitted through the elastomer and converted to an electrical signal. Using the MATLAB real-time extensions, closed-loop control of finger and hand have been investigated. Low-level control of force and position uses a task function approach with a calibrated finger model to estimate unconstrained motion. Medium-level control coordinates finger and knuckle actuators to control grasping. Data from the slip sensors is used to reactively trigger changes in grasp forces. Slipping can thus be prevented or deliberately controlled. The hydraulic proportional valves used for this control have limited bandwidth with deadband and hysteresis. A prototype electromechanical valve has therefore been developed for high bandwidth vibration damping. With a sliding mode approach, dynamics up to 6 Hz have successfully been controlled. For grasping and manipulation in poor visibility, we have developed a supervisory grasp planning system using blind grasping. Finger actions are sequenced to contact the object and estimate its geometry. Unsuccessful grasp attempts provide further information on object mass and friction. Geometric and semantic object descriptions are developed and used to reactively sequence grasping commands to the medium-level control. The gripper can thus grasp and manipulate without teleoperation and without vision. To operate the system, a Windows-based graphical user interface is employed. Windows can be dynamically opened and sized to show the current gripper configuration, the contact forces for each finger, the pressure commands to each valve, and to command teleoperation or blind grasping actions. The first Amadeus prototype is now complete, and we are currently developing a second for deployment on a robot arm and for evaluation by scientific and offshore users.